Okay, so welcome to class 21, which was discussed on 2nd March. So for next few days, we will be looking at the foundational aspects of StatMech. So till now, what has been going on is that after a very brief overview of thermodynamics, what we started is essentially the core assumptions of statistical mechanics being the ergodic hypothesis, postulate of equal a priori probability. The ergodic hypothesis was important because uh, using that, when one could say that whatever one calculates in the ensemble picture using statistical physics, that will be equal to the time average of quantities which one measures in the lab. But we shall also discuss some other quantities, and then we applied these. We developed the idea of microcanonical ensemble. This then we figured out how to calculate the total number of states, microstates, at least for some simple systems. And we also discussed about, from the microcanonical ensemble, we use the idea of canonical ensemble, and which considered a system is an equilibrium with a larger reservoir, and again calculated PV equal to nRT using the canonical ensemble, and so on and so forth. We also discussed ferromagnetism, but all of this assumed that equilibrium has been reached, system as in equilibrium. But there can also be questions that if a system is left to itself in a non-equilibrium situation, will ever equilibrium be reached? What is the method? Why should we believe that the system will reach equilibrium? Because once equilibrium is reached, and one also assumed that in an isolated system, all the microstates would have equal probability of being accessed. Uh, where does that come from? I mean, it seemed that it came out of the blue in 1873. I mean, or maybe later. I don't know how it was developed. But I guess 1873, when Boltzmann wrote down S equal to KB log omega. But the question is, why should we take that? So the point is, there was some quite amount of some work which was done in the 1860s, which was an extension of the kinetic theory of gases, and those laid the foundations on which we could postulate uh, we could state the postulate of equal a priori probability, and so on and so forth, on which the concepts of statistical physics developed. So how is equilibrium reached? What is the mechanism of reaching equilibrium? What are the properties of equilibrium? Those are the topics of discussion for the next few classes. The other point is, when we started the statistical physics course, at some point I said, what is equilibrium? And that was discussed in a thermodynamic state, in a thermodynamic macroscopic context, which means that we basically said that physical properties as measured macroscopically, like pressure and temperature, density, they didn't change as a function of time. Moreover, but that's not a good enough condition. Moreover, we said that there should be no current in the system. There should be no thermodynamic current, no current of mass. There should be no current of momentum. uh, there should be no net current of energy or charge or whatever. So all over the system, it should be uniform. Now, this can be in the condition when the system is in contact with a reservoir or in absence of a reservoir, right? So because, I mean, we also work with systems like in this room, which is in contact with a reservoir. Okay, in this room you have AC, but if you left it to itself, it would be in contact with the reservoir, heat reservoir of Pune, whichever city you are in. So macroscopically, we discussed that there should be no current in the system. That is a condition of equilibrium. And the other point is, however, if there was a current in the system which was a driven system, there was some external conditions. Suppose for a bar of metal, there was temperature T2 on one end and temperature T1 on the other end, and it had reached steady state, which means there was a temperature gradient along x being suppose along the axis of the bar. That didn't change as a function of time. So that's a steady state because there was a current flowing. There was some heat current, some energy current flowing from one end of the bar to the other, though the temperature profile didn't change. But that's a steady state system. That's not an equilibrium system. There are macroscopic energy currents flowing into the system. Now, how would that manifest itself microscopically? So those are the questions which are going to discuss. So basically, we're going to discuss the properties of phase space density, and we'll show that it behaves like an incompressible fluid uh, as it evolves in time. And there are certain conditions which we could associate with equilibrium, where phase space density is uniform over space, not only space, but also the other degree of freedom being momentum. Of course, it should not change as a function of time. And thereby, because the density of phase space in equilibrium will remain uniform. So there are two things. Phase space density behaves like an incompressible fluid, is that the phase space density cannot change, right? And moreover, if it's independent of x, y, and z, right, then the system is in equilibrium, and from there we can get the postulate of equal a priori probability. So that's the so-called Liouville theorem. That's the foundations on which the microcanonical ensemble is defined. Moreover, we shall discuss that a system left to itself microscopically will evolve to an equilibrium condition in the and their entropy will be maximized, or some other quantity called H, which was first defined, that would be minimized, and so on and so forth. And yeah, so we shall also discuss the time evolution of non-equilibrium systems, which is through the Boltzmann transport equation, and so on and so forth. So that these are the broad topics, the foundations of StatMech, on which the equilibrium StatMech assumptions were based. And there's a method, there's an algorithm, there is a method to calculate various statistical quantities if the system is in equilibrium. For non-equilibrium, we don't have a general method to calculate the properties, general principles. But if a system is in equilibrium, we have a formalism. I was looking for the word formalism to calculate thermodynamic properties. But where did these formalisms, etc., come from? Or what are the physics on which these formalisms is based? Is what is the topic for the next few classes? So these questions that I have written down here are listed in also in Kardar chapter 3, but thereafter we are